Last few lectures we have dedicated to the discussion of equilibrium, equilibrium constant and effect of various factors on the value of equilibrium constant. Being a very important topic because it not only allows us to answer many questions qualitatively, but makes the process quantitatively, this concept is very important. From chemical systems to biological systems, the concept of equilibrium and equilibrium constant is required. For example, when we talk about the biologically important systems, maintaining the pH becomes very important. And therefore, the concept of pH also becomes very important. In today's lecture, we will focus our discussion on acids and bases and equilibrium concepts, as well as we will discuss a little bit about pH and how pH is related to activity of the hydronium ion, or can pH be related to the concentration of the hydronium ion. Let us discuss about these matters. First of all, let us talk about the Bronsted-Lowry classification of an acid. Let us take a look at the slide. According to Bronsted-Lowry classification, an acid is a proton donor. A substance which can donate a proton to another molecule will be classified as an acid according to Bronsted-Lowry classification. As seen in this slide, in this equation, Ha is an acid because it is a proton donor, and a base is a proton acceptor. That is, a substance which can accept proton from another molecule is a proton acceptor and it acts like a base. So, in the first reaction Ha going to H plus A minus, it is donating proton. So, therefore, Ha is an acid, and B is accepting a proton, therefore, B is a base. Let us discuss a little more about this. HCl, according to this classification, is an acid because it can donate a proton, that is hydrogen ion. We know that when HCl is dissolved in water, it dissociates into H ions and chloride ions. So, therefore, HCl is capable of donating a proton to another molecule. And that is why, let us take a look at slide, the statement that HCl is an acid because it can donate a proton. H ion is called as a proton. If we take another example, that is of ammonia. Ammonia is base because it can accept proton from another molecule and it can form ammonium ion. So, these examples justify the definition of Bronsted-Lowry classification that an acid is a substance which can donate proton. Like in HCl, HCl is donating a proton, so HCl is an acid. And ammonia can accept a proton, therefore it is a base. In the Bronsted-Lowry classification, there is no mention of the solvent. The solvent can be any. And if we are talking about the biological systems, the biological systems are mostly in aqueous media. Therefore, the discussion of water as a solvent becomes very, very important. In most of the examples which I am going to take in further discussion, we will take water as the solvent, because many reactions take place in aqueous media, especially the biologically important reactions take place in aqueous media. So, let us talk about acid-base equilibria in water. Let us consider this equation or this reaction in which Ha is interacting with water and donating a proton to water, forming H3O plus and A minus, all are in aqueous solution. And this H3O plus is called hydronium ion. What Ha has done? It has donated a proton to water and water has become hydronium ion, it has become charged and left over is A minus. So, we say that Ha is an acid and A minus becomes the conjugate base of the acid Ha. Acid is Ha and its conjugate base is A minus. This is how we will classify these. An example of this type of reaction is dissolution of HF in water. H will donate its proton to water and it will form H3O plus and F minus. Here HF is an acid and F minus, that is fluoride minus, is its conjugate base. So, this dissolution of HF into water, what it has produced? It has led to the formation of hydronium ion and it has formed fluoride ion. Now, we have thoroughly discussed in previous lectures how to write an expression for equilibrium constant. We will apply that concept over here and write an expression for equilibrium constant. How do we write equilibrium constant? Equilibrium constant is equal to the product of activities of the products raised to the power by their stoichiometric number divided by the product of the activities of the reactants raised to the power by their stoichiometric numbers. Keeping that in mind, let us go to slide and write an expression for the equilibrium constant for this process, this reaction. The equilibrium constant for this reaction is equal to K is equal to activity of hydronium ion into activity of, or let us say we write for this upper reaction, K is activity of hydronium ion into activity of A minus divided by activity of Ha into activity of water. This is an expression for equilibrium constant for this reaction. This reaction corresponds to the dissolution of an acid into water. And also it is worth noticing again that equilibrium constant is expressed in terms of the activities. water is in excess over here. Mostly when the solution is very, very dilute, generally we deal in aqueous solution, we deal with dilute solutions, and the activity of water is taken as 1 unity. So, by taking the activity of water as unity and consuming it along with the K equilibrium constant, I can write another constant which is called the acidity constant. When I convert this expression into acidity constant, this A activity of water is consumed into this by treating activity of water to be equal to 1. So, the acidity constant Ka becomes activity of hydronium ion into activity of A minus, which is the conjugate base of the acid Ha, divided by the activity of Ha. We have taken activity of water to be 1. Acidity constant is a very important quantity, because this acidity constant, as we will realize later on, gives us an information on the proton donating power of a molecule. Let us discuss further how it gives information, but before that, now let us consider a base. A base, when dissolved in water, it will accept a proton from water and will form hydroxide ion. In the same manner, if B is a base, then its conjugate acid is Hb plus. So, once again it is worth noticing over here that when this base is dissolved in water, then after accepting the proton Hb plus becomes the conjugate acid of the base B. Let us take an example of this kind. Ammonia, on dissolution with water, it will accept a proton from water, form ammonium ion and hydroxide ion. And obviously here, if NH3 is a base, NH4 plus is its conjugate acid. Ammonia acts as a base, ammonium ion acts as an acid, and we will soon discuss whether this acts as a weak acid or it acts as a strong acid. That we will discuss a bit later. Now, what happens is, since this NH4 plus itself is an acid, so the Bronsted acid Hb plus, NH4 plus is a type of an acid Hb plus, and Hb plus itself can participate in a proton transfer equilibrium, because as we discussed earlier, Hb plus or any molecule which can donate proton to another molecule will act as an acid. Therefore, if we have Hb plus type of species in solution, which is Bronsted acid, can also participate in proton transfer equilibrium, as we can see in the next example. Hb plus aqueous is plus water is forming H3O plus B. So, you see what we have here is Hb plus is donating proton to water, and what we are getting is H3O plus B, which in the example that we took over here, the ammonium ion can lose the proton to water, resulting into hydronium ion and ammonia. So, the point to be noted from this slide is that when you dissolve a base into water, it forms its conjugate acid, and that conjugate acid can further participate into a transfer of proton transfer equilibrium, and set up another equilibrium. That is, you see that the Bronsted acid, whether you talk about Hb plus or NH4 plus, it will donate proton to water and will form hydronium ion. We need to keep all these kind of equilibria in the mind. Let us take a look at the slide. The general form of Bronsted equilibrium is that you have an acid and you add water. An acid, Bronsted acid, will donate proton and you have this kind of expression, reaction. When we write an expression for acidity constant, it will be activity of hydronium ion into activity of the base divided by the activity of the acid. And we are taking the activity of water to be 1 because water is in excess. Ka is the acidity constant. Depending upon the type of acid, the value of Ka is going to be different. Whether we are talking about NH4 plus or we are talking about HF or HiO3, the value of Ka is going to be different. Let us take a look at the slide. The value of acidity constant for ammonium ion is 5.6 into 10 raised to the power minus 10. And the value of Ka for HiO3 is 0.16 at 298 Kelvin. Please note that Ka, which we are calling as acidity constant, is an equilibrium constant, and the value of equilibrium constant does depend upon temperature. Please recall the Van 't Hoff equation, that whether the equilibrium constant will go up or go down in its value with increase in temperature is decided by the exothermicity or endothermicity of the process. So, going back to the slide, the values of Ka have to be given at a particular temperature, because as I said, this Ka is actually an equilibrium constant and therefore it is temperature dependent. Ka is very small, you see 5.6 into 10 raised to the power minus 10 for ammonium ion, and it is high compared to this. 0.6 is very high for HiO3 at 298 Kelvin. And since Ka has been introduced, it makes a sense to introduce another simpler quantity which is based upon Ka, and that is pKa. pKa is negative logarithm of Ka. This is log base 10. And when you substitute these Ka values for NH4 plus and HiO3, what do you get? We get pKa is 9.25 for ammonium ion and 0.80 for HiO3. You see there is a negative sign here, and that takes care of the very small value of Ka, and since Ka for ammonium ion was very small, you see the pKa value is turning out to be very high. So, we can make a general statement here. If pKa is very high, the corresponding Ka is going to be small. In other words, if pKa is very high or Ka is very small, it is a poor proton donor. Its proton donating capacity or ability to other molecule is not very good, not very high. So, you see here pKa for HiO3 is small, very small compared to the pKa for NH4 plus, and that is why the Ka value for HiO3 is very high when you compare this value with the Ka value for ammonium ion. And since Ka is an equilibrium constant, and therefore these values can also be manifested in delta G naught. Delta G naught is minus RT log K, and if you convert this natural log into log base 10 and put minus log Ka as pKa, do this transformation and substitute over here, we end up with this relation 2.303 RT pKa. So, from pKa we can also talk about the reaction, standard reaction Gibbs energy. So, the concept of pKa or Ka is very important, because essentially Ka defines how much hydronium ion is present in the solution and how much, of course, is the amount of base and acid also present in the solution. Now, let us discuss autoprotolysis and pH. Water is a very important solvent. I have been highlighting the significance of water again and again. This is because although water appears to be simple, but when we try to look at the structure of water and see how the structure of water is altered when a solute is added to it, it brings complications. And water is a very important solvent when we talk about biological systems. Let us take a look at slide. Water is amphiprotic solvent or amphiprotic molecule, which means that it can act as both an acid and a base. Water. Let us take a look at water. It can accept a proton, it can also donate a proton, therefore, it is amphiprotic. That is what we are talking about. What it means is, if I take two water molecules, or if I mix water with another molecule, depending upon the type of the molecule, it may accept proton or it may donate proton. Like I can take its example with HF and I can take its example with ammonia. So, therefore, whether it will accept proton or it will donate proton, it depends on type of molecule, type of another molecule. Let us go to the slide. We take an example of HF dissolution in water. What we have is H3O plus and forming fluoride ion. water has accepted a proton, therefore it has acted as a base over here. On the other hand, if I choose another example, for example, if I take NH3 aqueous and take water liquid, what I get is NH4 aqueous plus OH minus aqueous. In this case, water has donated a proton. You see here, when you see, it has donated a proton to ammonia and formed ammonium ion. Therefore, it has acted like an acid over here. And that is what I was talking to you, that water is amphiprotic. It can act as an acid or it can act as a base. Let us take water liquid plus water liquid. Water itself can act as an acid or it can act as a base, because water can accept a proton or water can donate a proton. If it accepts a proton, what I have is this hydronium ion, and if it donates a proton, I have the hydroxide ion. This is called autoprotolysis of water. Water itself is acting as an acid, it is acting as a base. And autoprotolysis constant, if I write actually K for this, it will be activity of H3O plus into activity of OH minus over activity of water squared. Now, if I take activity of water to be 1 and consume it along with K, I will write another constant which is called Kw, and this is activity of H3O plus into activity of OH minus. Let me now go back to the slide, and this constant Kw is called autoprotolysis constant of water, which is activity of hydronium ion into activity of hydroxide ion. And similarly, I can write pKw, which is minus logarithm of Kw. At 25 degrees centigrade, the value of the autoprotolysis constant of water is 1.008 into 10 raised to the power minus 14. So that means pKw comes out to about 14, and since K is so small, 10 raised to the power minus 14, let me write here Kw is 10 raised to the power minus 14 at 25 degrees centigrade for this reaction. That means the extent of ionization is very, very small. That is what is commented over here. At 25 degrees centigrade, the autoprotolysis constant of water is 1.008 into 10 raised to the power minus 14, indicating only a few molecules are ionized. And since in water the activity of hydrogen ion and activity of hydronium ion are same, if we look at this equation, the 1:1 ratio they are produced, activities are same, and therefore, I can use this equation to calculate the activity of hydronium ion. Since they are same, I can, let us look at the slide, activity of hydronium ion will be just Kw square root, which will come out to be 1.004 into 10 raised to power minus 7 at 298 Kelvin. If we note down the activities of hydronium ion in 1 molar HCl, it is 0.81, and pure water it is 10 raised to power minus 7, we just discussed, and in 1 molar activity of hydronium ion is about 10 raised to power minus 14. See, the activities, if I say 1 molar concentration, activity is different because activity coefficient has to be included. And here activity is 10 raised to power minus 7. Here activity of hydronium ion is 10 raised to power minus 14. Therefore, there is a need to develop a new simpler scale which should depict the value of activity of hydronium ion in a simpler manner, and that is pH scale. pH scale is very important, and that pH scale we will discuss in the next lecture. So, the discussion in this lecture on the weak acids, strong acids, autoprotolysis and pH we will continue, and again use the concept of equilibrium in getting more insights into these kind of reactions in the next lecture. Thank you very much.